begin. So good evening, everyone, or good afternoon, depending on what time you want to, or what word you want to say at this time. It is 5 p.m. Jamaica time. So the concept of solubility product is all contained under our concept of solubility, right? Can anybody just describe what solubility is? You don't have to give an exact definition, but what is solubility? We have to understand that before we start talking about what a solubility product can be. Any takers? There are three capabilities. Go
Ability
ahead.
for like a solid to dissolve in a solvent.
To form a solution. Okay. Okay. Okay, so one of the things that we need to note here now, right? In CSEC, we said that we have things called soluble salts and insoluble salts, right? What's the difference between soluble and insoluble salts?
Um, one can dissolve in water and one can't.
Okay. So one can dissolve and one can't. No, rubbish. Both dissolve, but one has a higher solubility product than the other. All those salts that we said don't dissolve, they all dissolve, but their solubility product is really, really, really small. Anything that touches a solvent in which it can, well, that is ionic, right? Any ionic substance that touches a polar solvent does dissolve in some amount of way. Even if it's only two ions enter the water, it dissolved. Right? So every single salt can dissolve within polar solvents, but is what we call sparingly soluble salts or insoluble salts. They have extremely small solubility products. So to our eyes, nothing has dissolved, but chemically, there are ions in solution. Make sense?
Yes, sir.
All right. So, solubility is the fundamental concept in chemistry that describes the ability of a substance, the solute, to dissolve in a solvent to form a homogeneous mixture called a solution. Right? So, this process typically involves the attraction between molecules of the solute and the solvent, meaning like dissolves like. A nonpolar solute can dissolve in a nonpolar solvent. Right? A polar solute can dissolve in a polar solvent, or an ionic solute can dissolve in a polar solvent. Alright? Really, really simple. So the maximum amount of solute, it can be described as well as the maximum amount of solute that can be dissolved in a solvent under specific conditions such as temperature and pressure. It is usually expressed in terms of grams of solute per 100 grams of solvent or in molarity. Right? So we normally describe it in molarity, in concentration. How many moles of this exist within this amount of volume? Right? So we're talking about solubility now. Get in the headspace of thinking about ionic compounds or multitude of salts, right? And the fact that they release themselves as ions within solution. And we're trying to determine the concentration of these ions in solution. Okay? So the factors that affect solubility, we would have looked at these long before in fourth form
Sir,
chemistry. Go ahead.
yeah, share your screen by the way.
I have not been sharing my screen. Oh my, look at that. Pretty PowerPoint, and I haven't shared my screen. Let me end this and then reshare. Everybody can see it now?
Yes, sir.
Alright, so we're talking about solubility. These are two definitions that I just went through. Alright? If I sound a bit muffled, that's because my wisdom tooth is growing out, so it's kind of weird. Alright, and it hurts. So I'm just gonna try to move as swiftly as possible, right? Making sure that everything is brought across, as best as possible, right? So factors affecting solubility. We've looked at this in our own fourth form chemistry. If we haven't, that means we've seen it in third form or at least first form. In first form, the first thing I learned, I think it was the second topic I learned, was that solutes can dissolve, right, in something called a solvent to form a solution, and it depends on temperature and pressure, right? But you'd have looked at it in fourth form. What affects solubility? The nature of the solvent and the solute. Like dissolves like. Polar dissolves polar. Non-polar dissolves non-polar. Make sense? And everybody should know why. Okay? Temperature, in many cases, the solubility of solids in liquids increase with temperature, while the solubility of gases in liquids decrease with temperature. Right? We're not talking about creating different types of foams, etc. So we're not going to talk about solubility of gases in liquids. We're going to focus on solids in liquids, okay? So we know the concept of temperature and how it affects solubility, yes? If we increase the temperature, what happens to the solubility? Does it increase or decrease? Shanique, Wakanda? Increase or decrease?
Repeat the question, sir.
If we increase the temperature, does solubility increase or decrease?
Increase?
Okay, it does increase, right? Just like how if you had a cup of cold water and you put sugar in it, it won't dissolve. But if you boil the water, all the sugar will dissolve, and then the water is able to hold even more sugar. Right? So as you increase the temperature, the solubility increases along with it, right? So more solids can be trapped within the liquid or can be dissolved in the liquid. Right? Pressure is the same thing for gases in liquids, but we're not going to discuss pressure at this level. Okay? So we're mainly going to look at the nature of the solvent, right? And the solvent and the solute and the temperature. Types of solutions. You need to know the types of solutions as well. Saturated solutions. A solution in which the maximum amount of solute has been dissolved at a given temperature and pressure. That is what we call a saturated solution. An unsaturated, okay, that basically means that nothing can be dissolved further, right? So saturated means that nothing can be dissolved more into a solution at that given temperature and pressure. For unsaturated, it basically means that there's less solute than the maximum amount that the solvent can hold. So you can dissolve more. Alright? You can dissolve more stuff into the solvent. And then supersaturated, which we will be looking at, and it concerns us a lot in solubility products, supersaturated solutions. A solution that contains more dissolved solute than would be possible under normal conditions. So these solutions are unstable and can precipitate excess solute if disturbed, right? So supersaturated solutions now hold more solute than the maximum under normal conditions. Any questions?
No, sir.
All right. So the solubility product KSP, right, is the equilibrium constant for the dissolution of a sparingly soluble salt in water. You see this part? They might ask you to define KSP, right? There are actually only like 4 types of questions that can come for KSP. So I gave you all 4 types of questions and we're gonna work them. Well, actually they can derive more no. But we're gonna talk about that. So the solubility product is the equilibrium constant for dissolution of a sparingly soluble salt in water. A sparingly soluble salt in water. Note that definition. Note that definition. Alright? What is the equilibrium constant Kc? Can somebody define the equilibrium constant Kc? What is Kc? Nobody? Good evening to those who joined. Sukanaya or Kadane, you'd like to attempt? What is the equilibrium constant Kc? We need to work on how to define every single one of them, you know. Must be able. Go ahead. I heard somebody raise their hand, I think.
Kc is the equilibrium constant expressed in terms of concentration.
Lovely. Right? So we must be able to define every single K. Right? So we have around 1, 2, 3, 4. We have around like 5 Ks left to know. Alright? So including K stability, which is at the end of the syllabus. Literally last topic. Right? So we have this to look at. So we're looking at this equilibrium constant now specific for dissolution of a sparingly soluble salt in water, which represents a product of the concentration of the ions in solution raised to the power of their stoichiometric coefficients. Right? Which is painfully obvious. Everybody's fine?
Yes, sir.
Alright. And note that they must be aqueous and it must be coming from a solid. Because we're talking about a sparingly soluble salt. Solid. Right? In water. Aqueous it must be. Okay? So let's look at this now. The core principles of the solubility product now. Solubility product KC, well KSP rather, we'll look at this already. So it is defined as equilibrium constant for the dissolution of a sparingly soluble salt in water, and it represents all of this. Alright, we'll talk about that. So the KSP expression reflects the balance between the dissolution of a salt and the formation of a solid. Remember, it's an equilibrium constant, you know. So if we have a beaker of substance, right, of a solvent, right, and we add a solid salt in there, right, if we look at the surface of the salt, so let's zoom in on the surface of the salt, right, the surface itself, ions itself will themselves will be leaving in the solution, into the solution per se. Or let me put solvent, right, and this is the salt itself, right? And then we have some ions will now precipitate back to the salt. So this moving right back and forth between solvent and salt, between solid and aqueous, is physical dynamic equilibrium, which we discussed yesterday. Right? So it's really simple like that. So it's a type of equilibrium, and we're describing using KSP the equilibrium of this system that I drew right here. Okay? So the larger the solubility product, the more solvent we have dissolving. The smaller it is, the less solid we have dissolving. Okay? The solubility product arises from the establishment of this dynamic equilibrium between the dissolution of salt, the forward reaction, and the precipitation of the salt, the reverse reaction. Okay? At equilibrium, the rate of dissolution equals the rate of precipitation, resulting in a constant concentration of ions in solution. And that is what we describe in KSP. Remember, if there are any questions, you can just raise your hand and go. So from here, the raise hand notification, I'll just let you go. Okay? A saturated solution. Remember, what we're looking at is the principles at the core of this topic, you know. KSP is at the core of the topic. The solubility product itself, alright, dynamic equilibrium is at the core of this topic. Saturated solutions are important to this topic as well. A saturated solution is one in which the maximum amount of solute has dissolved under specific conditions, temperature and pressure. Right? Temperature or pressure, but we're looking at temperature here. The concentration of ions in a saturated solution remains constant due to dynamic equilibrium. is being established, right, between dissolution and precipitation. Now, if you have an unsaturated solution, it's not going to work. It's not going to work. No. We must be able to prepare a saturated solution, which our syllabus tells us that we must know, and it is constantly appearing on our past papers. How do you obtain the KSP experimentally? I want you guys to go and research that. Obviously, I can tell you, but I want you to find it, because when you find it, it will be easier for you to understand and you will retain the information a bit better than when somebody comes and give you the steps, right? So when you find it, I would like you to send it in the, well, you can send it in the WhatsApp group if you'd like, all right? Or you can explain it to me to see how best you can explain it. Usually you need to explain it in around 6 steps. So find 6 fundamental steps to actually determine the KSP experimentally. One of them is forming a saturated solution from a supersaturated solution. So we need to know how to do that. Okay? An important part of it as well is the ion product, Q. Now, this is different from the Q that we saw in KC. So the ion product Q is a measure of the relative concentrations of ions in a solution at any given time. So it's really, really simple. When it's not at equilibrium, it is Q. If it is at equilibrium, it is KSP. Right? Same thing with the concentrations in KC. When you're looking at KC and it's not in equilibrium, you actually calculated Q for that instant in time. Right? So it's the same thing here. The ion product at a specific point in time is Q. Right? And if that specific point in time is equilibrium, then it is KSP. Alright? So it's using the same equivalent expression as KSP, but with the actual concentrations of the ions present. Okay? When Q equals KSP, the solution is at equilibrium, right? And is saturated with respect to the solute. If Q exceeds KSP, the precipitation occurs, right? So precipitation will start to occur until equilibrium is reestablished. And this is what occurs in supersaturated solutions, right? We have more ions in solution than the maximum amount, because that is what supersaturation speaks to. That means that Q exceeds the KSP of the specific ionic compound, right? So the Q exceeds the KSP of the specific ionic compound, therefore precipitation occurs. And we're going to see that in the next line, right? The common ion effect, right? The solubility of a salt can be affected by the presence of a common ion in solution. According to Le Chatelier's principle, if a solution hardly contains one of the ions of the salt being dissolved, the solubility of the salt generally decreases. Note that if a solution hardly contains one of the ions of the salt being dissolved, the solubility of the salt generally decreases. This occurs because the common ion shifts the equilibrium towards the side of precipitation. Any questions? Any questions between this slide, the ionic product, and the common ion effect? I want you guys to make questions and ask the questions now. But let's explore the common ion effect actually. I want us to explore it. Why is this video not videoing? Alright. Tell me if it is echoing. Or tell me if you can hear it as well. I mean, that's how you tell if it's echoing.
Addition of a compound with an ion that is in a particular...
Is it echoing?
No, it's okay.
saturated solution is commonly referred to as the common ion effect. I would like to demonstrate the common ion effect to you. What I have is a saturated solution, and it's important that we understand that in order for this to occur, the solution must be saturated. I'm going to take a saturated solution of potassium chloride, and I'm going to put that in a beaker. Now, I'm going to add a common ion to this. The saturated potassium chloride is approximately 4 to 5 molar, so that we have a considerable concentration of both potassium and chloride ions. In order to get the common ion effect, I'm going to add a sample of 12 molar hydrochloric acid solution. The 12 molar hydrochloric obviously is very heavily concentrated in chloride ions. As I add this, watch the beaker and you will see the reaction take place. Now, this is an example. This is an example of a reaction where we are sharing an equilibrium shift. By adding the common ion, what we are doing is precipitating the less soluble of the two compounds. With potassium chloride, if we go over to the board, if we go over the fact that potassium chloride is approximately 4 molar, we will see that the common ion, the chloride ion, is going to precipitate the potassium chloride, forming crystals, clear crystals of potassium chloride, which settle to the bottom of the beaker. So we have used Le Chatelier's principle, shifting the equilibrium by adding one of the products and causing a shift back to the formation of the solid potassium chloride.
Everybody understanding that so far? Thus far, is everything fine? Do we understand what happened a while ago? Somewhat.
Certain extent.
Okay, explain it to me. So since it's to an extent, let me hear where we went wrong. Or how much we understand so far. What do you understand so far?
Sir, that we had to use a saturated compound to begin with,
Mm-hmm.
and then I believe it was what hydrox. Wait, no, I'm not entirely sure. I didn't get what he put inside of the beaker
So he
after.
had potassium chloride, yes?
Yes, sir.
Salt. It dissolves to give us potassium. That doesn't look like potassium. That doesn't look like potassium either. Potassium ions plus the chloride ions in solution, yes? Aqueous, of course.
Yes, sir.
Lovely. And what he did was added, right? So we're adding now HCl, which concentrated HCl, right? Which is now this is saturated. So let me just put it saturated, right? So you added concentrated sulfuric acid, not sulfuric acid, hydrochloric acid. Said sulfuric because sulfuric is a really common acid to use, right? And then what we have now is creation of hydrogen ions plus the creation of chloride ions in solution. Can you explain it now?
Sir, so basically we have the dissolving and forming of potassium chloride and hydrochloric acid happening. Basically.
Okay. So what we have mainly, right? Remember that we have the potassium chloride existing within this dynamic equilibrium as a saturated state, right? So saturated with the ions of the potassium chloride. Notice we never really see any solid potassium chloride, right? So most of it dissolved, okay? So what he did was add hydrochloric acid, concentrated hydrochloric acid to an already saturated solution. And it produced a common ion. So notice that both of them have chlorine. Common ion effect, that is what it's called. So he produced a common ion. And we increase the concentration of chloride within the solution, obviously, because we're adding hydrochloric acid, so we increase the concentration of chloride in the solution, right? Make sense?
Yes, sir.
So what does Le Chatelier's principle state about this? I want you to get it. I don't want you to. Go ahead.
Is it that when there is a higher concentration of a common ion that it will be in the
No, no,
reaction
no,
will
no,
be.
no, no, no. Hold on. Don't use the common ion effect. Just use Le Chatelier's principle. Go ahead. Just use the principle. Just look at this first equation and just use the principle. Leave the common ion out of it. So we're saying that chloride ion concentration is increasing. So what happens? Just use the principle. Go ahead, man. You can do it. I believe in you. I'm cheering you on. Nobody else wants to help?
Was the equilibrium disturbed, sir, because of the excess chloride ions?
Yes.
So there was a shift then to like the other side, the
There was a
opposite side.
shift. Yes, yes, yes. There was a shift, and the equilibrium shifted to the left, right? Creating the solid salt, and that's why it's precipitating out of solution. Everything is clear now?
Yes, sir.
So everything is clear now. So because we added the common ion, right, to the parent solution, it increased the number of chloride ions in the solution overall, which shifts the equilibrium to the left, right, leading to the creation of more solid potassium chloride. So if we were to go back to this video, come on now, man, around here,
This, watch the beaker, and you will see
he's adding
the
the
reaction
common
take
ion,
place.
and the salt will
Now, this is an
precipitate
example.
due to Le Chatelier's principle.
This is an example of a reaction where we are sharing.
So the salt is precipitating out of solution. Remember, it was clear already, and now it becomes cloudy because there are more solid particles within solution.
An equilibrium shift. By adding the common ion, what we are doing is precipitating the less soluble of the two compounds.
And the less soluble of the two compounds would obviously be the potassium chloride, because everybody knows that hydrochloric acid is extremely soluble. It's an acid, it's really soluble, right? So it's less soluble than the potassium chloride. Therefore, the potassium chloride will be the one that precipitates out of its solution. Make sense so far? Everybody's clear now?
Yes, sir.
Crystal clear? Okay. Seems as such. So what we're seeing, according to Le Chatelier's principle, if a solution already contains one of the ions of the salt being dissolved, the solubility of the salt generally decreases. So what we end up doing is decreasing the solubility of our salt, our parent salt, allowing our salt to now precipitate out of solution. And it's important to know these things, especially when you're going to do chemistry or science in general, right? Because some people add solutions and starts the precipitation are going and have no idea what's happening. Alright, after dash with everything. Imagine doing an experiment that takes like 40 days. Each day 26. And then you accidentally got add a common ion and you have to start over. So you have to remember these different things, alright? So you have stuff like that. So the last thing here is temperature dependence. In many cases, the solubility of salts is temperature dependent. Increasing the temperature often increases the solubility of salts, as it provides more energy for the dissolution process to overcome the lattice energy of the solid. However, this is not universally true for all salts. Some salts have such a high lattice energy, it won't work that easily, and some salts have varying structures that don't work truly dependent on temperature. But for now, at the Cape level, we'll just say all of the salts that we work with are dependent on temperature for their solubility. Does that make sense? Does this slide make sense? Talking about temperature and lattice energy and everything, does this slide make sense? I know that in earlier sessions we did describe lattice energy beautifully. What is lattice energy? Azriel, Kadane, Laquanda, Shani, Sukanaya. Sorry.
So,
Sukanya, go ahead.
lattice energy is the energy required to convert a mole of solid to gas.
So gas, interesting. You sure?
Yes.
You're sure?
Sir, is it the amount of energy it takes to break bonds between molecules?
Between what? You're sure? Hold on. I cannot believe my
What did
eyes.
I say? Did I say solid to gas?
Yes. You're talking about Wait, you're talking about what?
The lattice energy.
Uh-huh.
Um, Hold on 1 second.
The page them must skip though. Skip the page them for you. Cause if you don't remember, this is time to just go and get that information. Come and explain to me what lattice energy is.
It's the enthalpy change when 1 mole of an ionic solid is formed from its gaseous ions.
Lovely. So the energy change when 1 mole of the ionic compound is formed from their gaseous ions. We went through the not the Haber process, the Born-Haber cycle. Is the Born-Haber cycle? That entire thing, the Born-Haber cycle, yes. But we're just looking at that energy now. So the lattice energy is the energy that we need to overcome to break up the ionic solids to dissolve them in solution. So that's why when we increase the temperature, we are actually overcoming the lattice energy of the salt, right? And being able, and well, allowing it to be able to dissolve in solution, right? That's why more salt dissolves in hot water than in cold water, because hot water has more kinetic energy to break the bonds in the lattice. Make sense? Make sense, everyone? When we're done, we're supposed to be able to explain everything that we see around us chemically, from an organic point of view. Because this is beginners physical and organic chemistry. Right? Some basic school chemistry, Alright? Just take your time with the chemistry and it will treat you well. So are there any questions before we move on? Before we start moving? Everybody's fine so far, everybody's lovely. Hopefully everybody's lovely. Alright. So it seems that everybody's angry with chemistry. Remember that chemistry is ungrateful, if you don't practice her, she will not, actually stay with you, she's a very angry person, and chemistry is a difficult relationship to maintain. Alright? Okay, let's go. Question 1. What is the solubility product KSP expression for the sparingly soluble salt lead 2 chloride, PbCl2, given that lead 2 chloride dissociates to give lead 2 ions and chloride ions in solution? What's the answer? Somebody unmute and let me know the answer, no? Shouldn't take too long. And it's taking too long. I don't know what to feel about this. You guys are making me nervous. Making me really nervous. What's happening? What's the answer, guys? Oh, by the way, today we're working every question in this PowerPoint. Right? There's not a lot. There's a couple more. And that's it. Oh, and then we'll look at kidney stone formation. Let's go. Let's go. We have 4 more. So by now we need to get accustomed to the fact that, we're going to get questions every single time. So just bring a paper and a pencil with you. And a calculator if you so desire. But you will need it next week. That is if classes keep next week. But yeah. Nobody come with the answer yet? Come on, guys. Don't leave me hanging. No, I feel like it's spite, I feel like it's spite. Where's the answer? Kadeen, what's the answer? Kadeen? Lakonda, where's the answer? Bring the answer, come, please. And stop gatekeeping the answer.
It's in the chat, sir. Not mine, though.
It's in the chat? Alright, let me see. Sorry about that. Somebody could have said something, Alright, let's see. Shanika Varan. Oh! That is not the answer. That is a start, but it's not the answer. No, it's not a start at all. What is happening here? It is an incorrect start, but it is a start. And Shanique is the only person to show me anything. Therefore, congratulations, Shanique. You have won 3 points of respect. But where's everybody else? Nobody else tried it? Bring the answers rolling, man. Shanique, nice try, but fix the equation, man. Fix the dissociation equation. And then write a KSP expression. Alright, you're on the right track. Remember to use reversible arrows. Where are the answers, guys? We have 4 more questions or 3 more questions remaining. And the last question is not a short question. It's not well, it's short. Yeah, it's short. It's actually really short, actually. But yeah. Guys, we only have 20 minutes left. And you guys for a reason. We know the answer already.
Sir, hold on. Can you see what the KSP equation side, please?
Oh, no problem. But what were you saying upon now? So what we're required to do, is to write this, our KSP expression. That's what the question asks, That's why I was wondering if you guys being selfish, holding back.
Sir, could I try?
Okay.
Sir, verbally do, cause
verbally, well, sure. Do you guys see the slides moving or not?
no, sir, it's still on the
All right.
JSP, sir.
So there's an issue with the PowerPoint. I'm going to reshare. Okay.
Okay, sir.
Yeah, because I've been skipping the slides for years now. I haven't been skipping, so I'm gonna just close the thing and then reopen it. Okay, yeah, the PowerPoint has crashed, guys. See, when you never want to give me the answer, no, the PowerPoint crashed. Terrible people.
Sir, can I try verbally?
I wanted to write what you're saying, that's why. Give me a moment. I want to bring up the PowerPoint on a blanks, well, on the question screen, for me to write all the foolishness, you know? Not saying that what you're writing is foolishness, by the way. Well, it's either it's foolishness or it's right, but let's see if it's right. Let me know when you can see the PowerPoint when it's loaded. Let me know when you can see it, guys. Alright. You guys can see it now? We can see it now? Hello? Can we see it now?
Yes, sir.
Yes, sir.
Alright, lovely. Alright. So let's go. What you saying now? What you're saying now is the answer. Is you that right the answer? That's not the entire answer.
Sir, I'm not finished yet.
But you could say it. Let me hear. Let me just write what you have in the chat. You can continue saying what you have.
Sir, based on the sir, based on the formula that I was seeing before, would it be bracket the bracket, right? PV, and then the close bracket, the two outside.
The two outside, okay.
Would it be two outside?
The two as an exponent or just two outside?
It's the the exponent.
Alright.
Would it be two outside though? Hold on.
Is you telling me the answer now?
We can do 5? Maybe.
Plus,
So Kanye, you want help?
yes, sir.
Alright, go for it.
I had the top balanced equation, but I put just PB 2 plus in the concentration bracket, nothing on the outside. And then I have Cl minus in the concentration bracket and then 2 outside the bracket.
So the concentration of these ions squared. And that is right. You wouldn't have a squared outside, what is it, Kanya? You wouldn't have a squared outside because we only raise it to the power of the stoichiometric coefficient. In this case, it is 1. Right? So we don't put anything. If you raise anything to the power of 1 is itself. So it's fine. So everybody's fine with this?
Yes, sir.
Alright. Lovely. Next question. Calculate the solubility solubility product right, of silver bromide, if its solubility in water is measured to be 1.3 times 10 to the negative 5 moles per liter. Have fun. I know that you guys are bursting with excitement. Please don't answer all at once. You know, it's kind of rude when you answer all at once, so take your time. We have 15 minutes remaining in this session, but you know, take your time. All right. Does anybody know how to attempt this question? Does anybody know how to do this?
Nope.
Nope. All right. So one victim, right? I need only one of you victims, right? Subjected to chemistry, to tell me how you would approach this. How would you approach this in the exam? Go ahead.
Okay, well, I would create the equation, the KSP equation, and well, I have it written down here, and it look like it's a 1 to 1
Love
ratio.
that.
So 1.3 by 10 to the negative 5 mole per liter would be in silver bromide. So silver and bromine have the same amount of mole per liter, just said. So just substitute it into the concentration, and yeah.
So what's the answer?
I didn't work it out yet. I was just picking up.
Okay, lovely, lovely. Work it out, man, because you are right. You can explain it when we're done. Square that. That means that the KSP is equal to. Where's my calculator, man? So here's 1.3 times 10 brought to the power of negative 5. Alright, now we'll bracket all of that and we'll square it. What did you get? Hello.
1.69 by 10 to the negative 10 mole per liter.
You sure? Is moles per liter? Isn't it that?
Yes, sir.
Right. Or if it was dm cubed, because we use dm cubed and stuff like that, it will be dm to the negative 6th and more squared. Alright, makes sense. Okay. So everybody understand this?
Yes, sir.
You sure? Alright. Because if I was you, back in the time when I was doing it on, me would have lost at this point. I have no idea what is happening. But okay. Alright, lovely. It's good to know that you guys are all smarter than me at this point. Alright, so okay, so alright. The solubility product constant KSP for silver iodide is 8.5 times 10 to the negative 7. Calculate the molar solubility of silver iodide in water. Since you guys are having so much fun. Couldn't stop the fun, I wanted to give you guys a little bit more, fun to have. So somebody come talk to me now. Alright? How would you attempt this?
Sir, would it be like the opposite of the question that you just worked? Instead of like finding the solubility for the equation per se and then squaring it. In this case, you would find the square root of this because this is the solubility product constant. So all we'd have to do is just square root it, given that it's a 1-to-1 ratio. So
lovely. 1-to-1 ratio. So because therefore, right? So I have this expression, right? Therefore, at equilibrium, don't mind my writing, by the way. Ag is at X amount of molarity, right? And I is at X amount of molarity as well. Because a 1-to-1 ratio, so they must have the same concentration, not true? Therefore, 8.5 times 10 to the negative 17th power, that is a KSP, We're substituting everything now into the equation. Sorry about that. I think my thing is just always switching the thing. Alright? So, KSP, this is a KSP given to us, is now equal to, oh my, I don't know why this keeps on happening, X, alright? So you say that that is the concentration of Ag at equilibrium times X, which is the concentration of iodine at equilibrium, which is ultimately X squared. And in order to find X, we must square root X and square root the KSP. So therefore, X is equal to what? What is the KSP? Sorry, not what is the KSP, but what is the answer when we square root the KSP? My answer is 9.219 times 10 to the negative 9th power. What did you guys get?
Same thing, sir.
Alright. So 9 point. Let me determine how many significant figures are supposed to have. Around 2 though. Can I put 9.2 times 10 to the negative 10th power? Is the 10th power I saw? 9th power I saw. Wait, hold on. Yeah, it's the 9th power I saw, not the 10th power. Alright? So that is that, alright? Everybody's fine with that? Everybody's cool?
Yes, sir.
Alright. So kidney stone formation. So the KSP specifically has this type of application, right? The syllabus also has to do the application and qualitative analysis, right, and the qualification for kidney stone and formation, right? But we will look at the qualitative analysis, right? But for now, kidney stone formation. This is not something that you have to know thoroughly, Just need to explain that solubility product and kidney stone formation have some amount of, correlation. So solubility product KSP is directly related to the formation of kidney stones, specifically in understanding the precipitation of certain salts that can lead to the stone formation. Kidney stones, medically known as, right, nephrolithiasis, right, or renal calculi, are solid masses made up of crystals that typically form in the kidneys, but can also develop anywhere in the urinary tract. Okay, so just looking at something like that. So how it develops, here's how it develops, right? So calcium oxalate stones develop. So one of the most common types of kidney stones is composed of calcium oxalate. Calcium oxalate is sparingly soluble in water, and its solubility product KSP is relatively low. So when the concentration of calcium ions and oxalate ions in urine exceed the solubility product, right? These ions can precipitate out of solutions to form crystals. Over time, these crystals can aggregate and grow into larger kidney stones. Okay? So that's really the main part that we want to talk about. Everything else is just information that you can read if you want to read it, but you don't have to read it because it's fine. Alright? So you can look at those type of things and dietary modifications that people must make. Right? So if you continue to consume things with high levels of calcium, alright, and high levels of, well, you can find oxalate when you eat leafy vegetables and stuff like that, right? And if you especially eat a lot of salt and stuff like that, right? You can actually develop a high concentration in your body that may exceed the KSP. And if it exceeds the KSP of this specific substance, right, or any other substance, it doesn't have to be calcium oxalate, right? It can build up, right, and then precipitation can start occurring, right, via the common ion effect most times. Right, so the common ion effect is responsible for those type of things in the body as well. Right, so that is really it.